Most people see a world of objects and chaos, but Carl Friedrich Gauss saw a hidden symphony of numbers and laws that govern the very stars above us. Today, we dive into the life of the Prince of Mathematicians, a man whose genius was so vast it literally redefined the boundaries of human knowledge. Part 1: The Child of Brunswick and the Nature of Genius. Welcome to an in-depth exploration of the life of a man who didn't just study mathematics, he spoke it as his native tongue. We are talking about Johann Carl Friedrich Gauss, a figure so monumental that he is often placed in the same small circle as Archimedes and Isaac Newton. To understand Gauss, we must travel back to April 30, 1777, in the Duchy of Brunswick, located in what is now Germany. Gauss was not born into a lineage of scholars. His father, Gebhard Dietrich Gauss, was a man of the working class, a gardener, a bricklayer, and a canal digger. He was a stern man who valued physical labor and had little patience for the abstract world of books. His mother, Dorothea Benz, was a woman of sharp natural intelligence but had received no formal education and could barely read. This humble beginning makes the emergence of Gauss's genius even more startling. There is no biological or environmental explanation for how a 3-year-old child could correct his father's payroll math. As the story goes, Gebhard was sitting at a wooden table, sweating over the ledger for his laborers' wages. Young Carl, barely a toddler, watched him from the corner of the room. When Gebhard reached the final sum, the boy spoke up, "Father, the reckoning is wrong. It should be this." Upon rechecking the long columns of figures, Gebhard found that his son was exactly right. Gauss later joked that he knew how to reckon before he could talk. This incident reveals the core of his genius. He didn't learn math in the traditional sense, he perceived the structure of numbers as an inherent reality. In 1784, at the age of 7, Gauss entered the Catherine School under a teacher named Mr. Büttner. It was here that the most famous anecdote in mathematical history took place. Büttner, wanting to keep his large class quiet, gave them a task that he expected would take an hour: add every whole number from 1 to 100. While the other children began scribbling furiously, 1 plus 2 is 3, 3 plus 3 is 6, young Carl walked to the front of the room within seconds. He placed his slate face down on the teacher's desk and said, "Liget se," which in his local dialect meant, "There it lies." Büttner looked at the boy with skepticism, assuming he had simply given up. But when the slates were turned over at the end of the lesson, Carl's was the only one with the correct answer, 5050. Gauss had recognized a symmetry that no one else saw. He paired the first number with the last, 1 plus 100 equals 101. Then the second and the second to last, 2 plus 99 equals 101. He realized there were 50 such pairs, each totaling 101. The calculation was simply 50 times 101. In the language of the classroom, we would say the sum s equals the fraction with numerator n times in parentheses n plus 1 and denominator 2. For n equals 100, the result is 5050. This wasn't just a trick, it was the birth of the theory of arithmetic series in a child's mind. Recognizing that he had a prodigy on his hands, Büttner brought in an assistant, Martin Bartels, who was only a few years older than Gauss but shared his passion for math. Together, they exhausted the school's textbooks. Bartels helped secure Gauss an introduction to the Duke of Brunswick, Karl Wilhelm Ferdinand. The Duke was impressed by the boy's modesty and brilliance and became his lifelong patron. Without the Duke's financial support, the Prince of Mathematicians might have spent his life as a gardener or a bricklayer, and the history of science would be fundamentally different. In 1792, at the age of 15, Gauss entered the Collegium Carolinum. It was here that he began to question the very foundations of geometry. While his peers were memorizing Euclid's axioms, Gauss was wondering if those axioms were truly the only way to describe space. He began to suspect that the parallel postulate, the idea that parallel lines never meet, might not be a logical necessity. This was the first seed of non-Euclidean geometry, a concept so radical that Gauss would keep it secret for most of his life, fearing the backlash from traditionalists. By 1795, he moved to the University of Göttingen. It was during this period, at age 19, that he made a discovery that decided his career path. Since the time of the ancient Greeks, mathematicians believed that only certain regular polygons could be constructed using only a compass and a straight edge. Euclid had shown how to make a triangle, a square, and a pentagon. But for 2,000 years, no one could figure out how to make a 17-sided polygon, or a heptadecagon. On March 30, 1796, Gauss proved it was possible. He didn't do it by drawing, he did it by showing that the side length of a 17gon could be expressed through square roots of rational numbers. He showed that a regular polygon with n sides is constructible if and only if n is the product of a power of 2 and any number of distinct Fermat primes. This discovery was so precious to Gauss that he decided to abandon his studies in philology and dedicate himself entirely to mathematics. He even requested that a regular 17gon be carved onto his tombstone. Though the stonemason eventually refused because it would look too much like a circle, the discovery remained the hallmark of his early genius. This wonderful year of 1796 also saw him prove the prime number theorem, where he conjectured that the number of primes less than x is approximately x divided by the natural log of x. If you are enjoying this deep dive into the early life of the world's greatest mathematician, please take a moment to like the video and subscribe to the channel. Part 2: The Disquisitions and the Secrets of Number Theory. By the time he was 21, Gauss had finished his masterpiece, Disquisitiones Arithmeticae. Published in 1801, this book is often cited as the most important work in the history of number theory. Before Gauss, number theory was a collection of isolated observations and clever tricks. Gauss unified it into a rigorous science. He famously said, "Mathematics is the queen of the sciences and number theory is the queen of mathematics." The centerpiece of this work was the introduction of modular arithmetic. We use this every day without realizing it when we tell time. If it is 10 o'clock and we wait 5 hours, it isn't 15 o'clock, it's 3 o'clock. We say 15 is congruent to 3 modulo 12. Gauss formalized this notation. He stated that A is congruent to B modulo n if the difference A minus B is divisible by n. In his script, he used the triple bar symbol, writing A triple bar B mod n. This allowed him to solve equations that had baffled Euler and Lagrange. One of his greatest achievements in this book was the proof of the law of quadratic reciprocity. This theorem deals with whether a prime number is a quadratic residue of another prime. In simpler terms, it asks if a number can be a perfect square when working in modular arithmetic. Gauss called this the golden theorem. He was so obsessed with its beauty and complexity that he eventually provided 8 different proofs for it throughout his life, each looking at the problem from a different mathematical angle. The Disquisitions also contained the first rigorous proof of the fundamental theorem of algebra. While others like D'Alembert and Euler had tried, their proofs had logical gaps. Gauss showed that every non-constant polynomial with complex coefficients has at least one complex root. In other words, an equation of degree n always has exactly n solutions in the complex plane. He visualized this by treating complex numbers not just as symbols, but as points on a two-dimensional surface, now known as the Gaussian plane. Gauss's writing style was notoriously difficult. He followed the motto pauca sed matura, which means few but ripe. He believed that a finished mathematical work should be like a beautiful building. Once it is complete, the scaffolding should be removed so that no one can see how it was built. This made his work intimidating for other mathematicians, but it ensured that what he published was perfect and indestructible. He would often keep major discoveries in his personal diary for decades, only to reveal them when someone else claimed to have found them. For instance, he discovered the method of least squares during this time, which is the backbone of modern statistics and data science. It allows us to find the best fitting line through a set of data points by minimizing the sum of the squares of the vertical deviations. In spoken terms, we look for the minimum of the sum of in parentheses y minus f of x squared. While Legendre published a version of this first, Gauss had been using it since he was 18 to calculate the orbits of planets. This brings us to a major turning point in his life. In 1801, the mathematical world was rocked by the discovery of Ceres. An astronomer named Giuseppe Piazzi spotted a tiny object between Mars and Jupiter. It was the first asteroid ever seen, but after only 40 days of observation, it moved behind the Sun and was lost. Astronomers across Europe were desperate to find it again, but their methods for calculating orbits were too crude. They had too little data. Gauss took up the challenge. He used his least squares method and his deep understanding of conic sections to calculate the orbit of Ceres. He didn't just guess, he predicted the exact coordinates where it would reappear. When astronomers pointed their telescopes to that spot on December 31, 1801, Ceres was exactly where Gauss said it would be. This achievement turned him from a brilliant student into an international celebrity. He was soon appointed the director of the Göttingen Observatory, a position he would hold for the rest of his life. Part 3: The measurement of the world and the curvature of space. With his reputation solidified by the discovery of Ceres, Gauss moved into a new phase of his career that bridged the gap between the stars and the soil beneath our feet. In 1820, King George IV of the United Kingdom, who was also the King of Hanover, commissioned Gauss to lead a massive geodetic survey of the Kingdom of Hanover. To the outside observer, it seemed strange that the world's greatest mathematician would spend his summers trekking through marshes and climbing the peaks of the Harz Mountains. But for Gauss, this was not a distraction, it was a laboratory. The challenge of surveying is the challenge of precision over vast distances. How do you measure a straight line when the Earth itself is curved? How do you account for the tiny errors that accumulate when sighting from one mountain top to another? Gauss threw himself into the engineering side of the problem. He invented the heliotrope, a clever device that used a system of mirrors to reflect a concentrated beam of sunlight toward a distant surveyor. This created a tiny, artificial star on the horizon, allowing for measurements over distances of up to 60 miles with unprecedented accuracy. While Gauss was physically measuring the kingdom, his mind was exploring a deeper, more abstract territory. He began to think about the nature of surfaces. He realized that a surface, like the Earth, has an intrinsic geometry. To explore this, he developed what he called the theorema egregium, which translates to the remarkable theorem. This theorem is one of the most profound realizations in the history of geometry. Gauss proved that the curvature of a surface could be determined entirely by measuring angles and distances on the surface itself, without ever needing to look at that surface from a third dimension. To understand this, imagine you are a tiny ant living on a giant, inflated balloon. Gauss proved that even if you can never leave the surface of the balloon to see it from the outside, you can still figure out that your world is curved just by measuring triangles. If you draw a triangle on a flat sheet of paper, the sum of its internal angles is always 180 degrees. But on a sphere, the angles of a triangle add up to more than 180 degrees. This discovery laid the foundation for differential geometry. It was the direct ancestor to the work of his student, Bernhard Riemann, and eventually to Albert Einstein. Without Gauss's remarkable theorem, we would not have the mathematical language to describe a four-dimensional curved spacetime. During this same period, Gauss was processing the massive amounts of data coming in from the survey. He noticed that the errors in his measurements weren't chaotic, they followed a specific, beautiful pattern. Most measurements were clustered tightly around the true value, while extreme outliers were rare. He formalized this observation into the normal distribution, or what we commonly call the bell curve. In the language of spoken math, the probability density function for this distribution is defined as f of x equals 1 divided by the product of sigma and the square root of 2 pi, then all of that multiplied by e to the power of negative fraction x minus mu squared over 2 sigma squared. Whether you are measuring the height of a population, the accuracy of a factory machine, or the fluctuations of a stock market, you are using the tools Gauss perfected while surveying the hills of Germany. Gauss's life during the 1820s was a grueling mix of high-level theory and brutal physical labor. He wrote to friends about the exhaustion of living in tents and the frustration of waiting for the sun to shine so his heliotropes would work. Yet, he never lowered his standards. He personally calculated every single data point from the survey, refusing to trust the work to assistants. He was obsessed with the purity of the data, a trait that defined his entire scientific life. If you are amazed by how a land survey led to the discovery of the shape of the universe, please hit the like button and subscribe. Your support allows us to continue these deep dives into the history of genius. Part 4: The Invisible Forces, Magnetism and the Telegraph. As Gauss entered his 50s, his focus shifted from the shape of the Earth to the invisible forces that surround it. In 1831, a young physicist named Wilhelm Weber arrived in Göttingen. Despite the age gap, The two men formed one of the most productive partnerships in the history of science. Their mission was to demystify magnetism. At the time, magnetism was seen as a mysterious fluid or a strange occult force. Gauss wanted to bring it into the realm of rigorous mathematics. He realized that to study magnetism, he first had to be able to measure it in absolute terms. He developed the first system of absolute units for terrestrial magnetism, expressing magnetic force in terms of the fundamental units of mass, length, and time. This was a revolutionary step. It meant that a magnetic measurement taken in Germany could be perfectly compared to one taken in London or Paris. To conduct these experiments, Gauss convinced the university to build him a magnetic observatory. But this was no ordinary building. Because iron interferes with magnetic needles, the entire structure was built without a single piece of iron. Every nail was made of copper, and the hinges were made of brass. Inside this non-magnetic sanctuary, Gauss and Weber spent years tracking the tiny fluctuations of the Earth's magnetic field. They established the magnetischer Verein, or magnetic union, which was one of the first international scientific collaborations. They coordinated observations from across the globe, creating the first truly global map of the Earth's magnetic intensity. But the most practical result of their partnership came in 1833. Gauss and Weber were looking for a way to communicate quickly between the astronomical observatory and the physics laboratory, which were about a mile apart. They strung 2 copper wires over the rooftops of Göttingen. By using a battery and a commutator to reverse the direction of the electric current, they could deflect a magnetic needle at the other end of the wire. This was the first functioning electromagnetic telegraph. It didn't use Morse code, that would come later, but it used a binary system of needle deflections to represent letters of the alphabet. While they saw it primarily as a tool for their own convenience, they recognized its potential. Gauss wrote that this technology would one day allow people to communicate across continents in an instant. They had effectively created the prototype for the modern telecommunications industry. The unit of magnetic induction is today called the Gauss in his honor. If you have ever heard of a degaussing coil used to clear magnetic interference from a screen, or if you know that an MRI machine is measured in Gauss or Teslas, you are seeing his legacy in action. Despite these world-changing inventions, Gauss's personal life was becoming increasingly isolated. His beloved first wife, Johanna, had died years earlier, and his relationship with his second wife, Minna, was professional but lacked the same warmth. He was a man who lived largely inside his own head, surrounded by books in a dozen different languages. He taught himself Russian at age 60 just so he could read the works of Nikolai Lobachevsky on non-Euclidean geometry. He was also deeply involved in the Seven of Göttingen affair. In 1837, the new King of Hanover revoked the state's constitution. 7 professors, including Weber and the famous brothers Grimm, protested and were subsequently fired. Gauss, ever the cautious conservative, did not join the protest, but he was devastated by the loss of his friend Weber, who was forced to leave the city. This period marked a darkening of Gauss's world, as he saw the political stability he craved dissolving around him. Part 5, The Final Proof and the Infinite Horizon. As Gauss moved into the final decade of his life, his home in the Göttingen Observatory became a place of pilgrimage for the next generation of mathematical giants. He was no longer just a researcher, he was the living embodiment of the Queen of Mathematics. Yet, even in his 70s, his mind remained as sharp as the edge of the straightedge he used as a boy. He spent these years looking back at his unpublished work and mentoring students who would go on to reshape the world of physics and logic. One of the most significant moments of this late period was the rise of Bernhard Riemann. When Riemann was preparing his qualifying lecture to become a lecturer at Göttingen, he submitted 3 potential topics to Gauss. The first 2 were standard, but the third was a radical exploration of the foundations of geometry. Gauss, usually conservative and reserved, chose the third topic. He wanted to see if this young man could truly grasp the concepts of n-dimensional manifolds that Gauss himself had secretly explored for decades. After the lecture, Gauss walked home in silence, visibly moved. He recognized that Riemann had finally built the formal mathematical structure for the non-Euclidean ideas Gauss had harbored since his youth but was too fearful to publish. Gauss's secrecy regarding non-Euclidean geometry is one of the great what-ifs of science. We now know from his private letters that he had fully realized that a consistent geometry could exist where the angles of a triangle sum to less than 180 degrees. He had even calculated the properties of hyperbolic space. However, he never publicly endorsed these ideas. He told his friend Friedrich Bessel that he feared the clamor of the Boeotians, a reference to the dull-witted critics of ancient Greece. He believed that the world was not yet ready to accept that the space we live in might not be flat. In his final years, Gauss also turned his attention to the fast Fourier transform. While the world would not truly appreciate this until the invention of digital computers in the 20th century, Gauss's notebooks from 1805 contain the core algorithm for breaking down complex waves into simpler components. This is the very math that allows your computer to compress a JPEG image or your phone to process a voice command today. He was solving problems for a digital age that wouldn't arrive for another 150 years. His personal life in these twilight years was one of simple, almost monastic routine. He woke up early, worked in his study until noon, took a walk around the Göttingen ramparts, and spent his evenings reading history and literature in his massive library. He was a master of many languages, including Latin, Greek, French, English, and Russian. Despite his international fame, he rarely traveled. He felt that as long as he had his books, his data, and a clear sky, he had the entire universe within his reach. However, his health began to fail in 1854. He developed an enlarged heart and suffered from chronic shortness of breath. Even as he grew weaker, he continued to correspond with colleagues about the latest developments in electromagnetism and astronomy. He passed away peacefully in his sleep on the morning of February 23, 1855, at the age of 77. The town of Göttingen mourned him as a fallen king. His legacy is not just a collection of theorems, but a fundamental change in how we perceive the world. Before Gauss, mathematics was often seen as a tool for calculation. After Gauss, it was understood as the very fabric of physical reality. He proved that the universe follows laws that are both beautiful and strictly logical. He bridged the gap between the ancient geometry of the Greeks and the modern physics of the 20th century. Every time a scientist uses a Gaussian distribution to analyze a clinical trial, every time an engineer uses least squares to build a safer bridge, and every time an astronomer calculates the trajectory of a distant comet, the spirit of Carl Friedrich Gauss is present. He was a man who started with nothing but a slate and a brilliant mind, and he ended by measuring the world, the stars, and the very concept of infinity. If this journey through the life of the Prince of Mathematicians has inspired you, please take a final moment to like the video and subscribe to the channel. Sharing this video helps us keep the history of science alive for the next generation of explorers. Thank you for staying with us through the full story of Johann Carl Friedrich Gauss.